Hi everyone, in this video I'm taking a look at question 13 part B of the Killara Extension 2 trial exam from 2020. So we're told that ABCD is a parallelogram and E is the midpoint of AB, and then we're given this diagram here. And we're asked using vectors to show that any line joining any vertex of a parallelogram to the midpoint of a side not passing through that vertex divides the opposite diagonal in the ratio 1 to 2. And that's a pretty confusing question, but thankfully they clarify that in this case what we're really being asked to show is that the line DE divides the line AC in the ratio 1 to 2. So let's take a look. So I've recreated the diagram. I've noted that E is the midpoint of AB, so these lengths here are the same. The kind of shorthand version of what we're being asked to show is that DE, this line DE, divides this line AC in the ratio 1 to 2. Or in other words, the division of this line AC is broken up such that the length from here to here, from A to F, would be 1. And the length from F to C would be 2. That's the ratio between those two portions. So I guess one way to think about it would be if AF was equal to 1, then A all the way to C would be equal to 1 plus 2 is 3. And I think that's a slightly more helpful way to think about it. We're comparing A to F and then A to C. So rather than A to F and F to C, I think it's more helpful to look at A to C as a whole. And actually, in generic terms, what we're really saying is that AC is equal to 3 times AF. Because we don't actually know if A to F is 1 or not. We're not given lengths here, but this is just a ratio. So really, it's just whatever AF is, AC will be 3 times as big. And because we're asked to use vectors, we can think of it in terms of AC vector being 3 times AF vector. And we'll use vector techniques to try and nut this out. Now, I think given that's what we're going to be focusing on, I think a natural starting point is to use a technique that maybe it's not very well known, but it is actually a technique. The technique I'm about to show is something that I used in another question I was asked, another vector question, and it's quite a handy technique. So I might actually give a link to that other question too, so that if you want more exposure to these kinds of questions, then looking at that one might also be helpful for you. But the basic idea is what we can say as a starting point is that vector AF will be equal to some fraction of vector AC. I'm just going to call it P, just for the sake of a letter. It doesn't matter what letter you pick. It's just as long as it's not, conflicting with all the other letters. P hasn't been used here, so I'm just going to say some value P times the vector AC, and that's where P is less than 1. So in other words, the vector AF is some fraction of the vector AC, and we can say that because AF and AC, those two vectors, lie on the same line, is how I'll state it. Basically, they have the exact same direction, and the only thing that differs between them is their length, and we know that AF has some shorter length than AC, and that relationship I'm just going to define with the letter P. And fundamentally, if we can find the value of P, then hopefully it's a value that lets us then conclude this relationship here. So suddenly, through this technique, the question gets reduced to find out this value P. So I think the next step we can do is think about vector AC in terms of these predefined vectors. So we were told that vector A, B, and D, C are both this lowercase a vector, and vector A, D, and B, C are this lowercase b vector, and it's probably going to be helpful to just state things in terms of those, just to maybe simplify some of the notation. So it's worth noting that AC vector, well, if I want to get from A to C, I can go from A to B and B to C. So I can say AC vector is equal to AB vector plus BC vector. And so from there I can insert the notations we were given. So AB vector is this lowercase a vector, and BC vector is this lowercase b vector. And so if I want to now take that and insert it in here, we can say therefore our AF vector, one way to write that, is equal to P times A vector plus B vector. And we can probably pause there in terms of this way of writing AF vector. And I guess the high level strategy now is to think, can we find another way to write AF vector so that whatever that other way is, we can equate it with this, and through typically some kind of simultaneous equation, simplify things so that we can work out what P must be. And so now we want to think, well, what other ways can we kind of get AF vector? And so just kind of looking at this diagram, we could say, well, to get from A to F, we could go from A to E, and then we could go from E to F. That's something we could do. So that could be a good kind of route to go to see where that leads us. So let's say AF vector we can write as being AE vector plus EF vector. And now let's kind of think about each of these one at a time and see, can we get those into this A and B vector notation. So AE vector is fairly simple. We can say AE vector is simply equal to A vector divided by 2, because we're told that E is the midpoint of AB. So whatever A vector is, AE vector is just half of it. So that's easy enough. Now if we focus on EF vector, we can almost use a very similar technique to what we started with, noting that EF and ED vector lie on the same line. So we can say EF vector is equal to some fraction, I've used P, so P, let's go Q, it's just the next letter in the alphabet, times ED vector. And the reason this idea is helpful is because when you go the full length, when you go the full distance, whether it's AC or ED, we know we can then make use of these existing vectors, because to get from E to D, we can go from E to A to D, and so on. That's the basic idea behind the strategy. So, on that front, we can say, well, okay, EF, which is what we want to put in here, is some value where, so I'll say where Q is less than 1. And again, it's because EF and ED, those two vectors lie on the same line. So now we want to think, okay, well, what's ED? So we can say ED vector, one way we can go from E to D is we can go from E to A, EA vector, and then we can go from A to D, AD vector. And if we want to go from E to A, well, that's it's basically the same as A to E, just the opposite direction. A to E we already worked out was A vector on 2, so that E to A is just negative A vector on 2, same vector, opposite direction. And then AD we're already given the definition as B vector. So therefore we can say that EF vector is equal to Q times, and maybe I'll just write this, the positive one first. So we'll go B vector minus A vector on 2. And therefore, we can conclude that AF vector is equal to our AE vector, which is A vector on 2, plus our EF vector, which we've just shown was Q, times B vector minus A vector on 2. Now, I'll probably have to turn over at this point, but the next step we're going to do is to say, okay, well, I've got one version of AF vector here. I've got another version of AF vector here. So I can set these two equal and see if we can simplify. So let's turn over and do that. So we can say, therefore, let's take our first AF vector, P times A vector plus B vector. P times A vector plus B vector is going to be equal to A vector on 2 plus Q times B vector minus A vector on 2. B vector minus A vector on 2. Now, at this point, it's helpful to expand everything out and then just kind of get the A vectors and B vectors by themselves and see what their coefficients are. So let's do that. So let's say we've got P times A vector plus P times B vector is equal to A vector on 2 plus Q times B vector minus Q times A vector on 2. And let's just, I've already got I've got A vector and B vector isolated, so that's going to, over here on the right hand side, let's say, well, what's going to be in front of A vector? It'll be this half minus Q on 2. That's all multiplied by A vector, and then plus the Q times B vector. And maybe I'll just rewrite this here just to make it really clear to do the comparison. Now what we can do is we can say by equating coefficients that whatever's in front of the A vector on the left hand side must be equal to whatever's in front of the A vector on the right hand side. And similarly, whatever's in front of the B vector, on the left hand side will be equal to whatever's in front of the B vector on the right hand side, because these are equal. So we can say, therefore, by equating coefficients, we can say that P must be equal to half minus Q on 2, and maybe I'll just call that equation 1. And we can also say that P is equal to Q, since that's what's in front of vector B. So I'll call that equation 2. And given this is so simple, we can just substitute 2 into 1. So where I've got this P, I can just write Q if I want, because P and Q are equal. So I can say, therefore, Q is equal to a half minus Q on 2. So if I bring this Q on 2 over, I'd have Q plus Q on 2 equals a half. So 1 plus a half is 1 1/2, or 3 on 2. So 3 on 2 Q equals a half. Now these 2's will cancel. So I'm really, if I bring the 3 down, I'm really getting Q is equal to 1 on 3. So therefore, if Q is equal to 1 on 3, if we go right back to where we started, well actually, if Q is equal to 1 on 3 and P is equal to Q, we can say P is equal to 1 on 3 also. And that, if we go right back to where we started, we know AF is equal to P times AC. And we want a relationship between AF and AC, so let's throw that in. So we can say, therefore, AF vector is equal to a third AC vector. And now just by bringing up the 3, and maybe I'll just reverse the order, I can say therefore AC vector is equal to 3AF vector. And remembering that that is what we needed to show. We needed to show AC vector is equal to 3AF vector, because that is the conclusion you can draw if DE divides AC in the ratio 1 to 2. That's kind of what we deduced at the beginning. AC vector equals 3AF vector. Well, that's what we've just shown. AC vector equals 3AF vector as required.
Sonic boom!
So I reckon that's it for that question. I reckon if you worked through all that, I reckon you get all your marks. And this question was actually in the context of this exam, it was worth 4 marks. So I wonder, I mean, yeah, it's a pretty tough question, so maybe that's fair. It's hard to know unless you look at the rest of the exam and see what kind of marks are being given for what. But as I mentioned at the beginning, this technique I've used where I kind of let one vector be some multiple of another vector when they're lying on the same line, that's a really useful tool to have in your toolkit, your vector toolkit. And if this is the very first time you're seeing this technique in action, and you want to get more exposure to these questions, as I mentioned, there's one other question I've encountered that I've had sent through to me on TickBoom where I had to use the same approach. So I'll share a link to that so that you can go take a look at that as well. It's a nice question. So yeah, I think that's the essence. I think once you kind of get that, well, actually, I think the key is realizing what a ratio of 1 to 2 really means, because then you realize it's this vector AC being equal to 3 times the vector AF, and then you just go, okay, well, let's find out more about AF, and that's where you use this technique I'm making reference to, and then you go, okay, well, let's find out about AC, and then find another way to write AF, and you're kind of just following this process, and eventually you're able to use simultaneous equations to get where you need to get to. So, I mean, hopefully that's all made sense, and you followed along, and that's something you could possibly do now that you've seen the technique. But yeah, try and find other questions that are like this if you want more practice, because yeah, I think it is the kind of question that you could expect to see on these 4-unit exams, particularly towards the end of the exam. I mean, maybe you could even see it on a 3-unit exam as something like maybe the final question. So yeah, there you have it for that question, and tick boom.